Welcome everybody on Zoom. You've got us here in the room outnumbered probably 2, 3 to 1. So it's good to see everyone joining, and we'll get started here in just a moment.
Not that many people there.
Format for tonight is as usual. We'll have our introduction and then a short presentation from the presentation from our speaker, and then we'll move into the club business announcements and a little bit of fun stuff. So should be a good meeting. And then,
Are you being pictured?
No.
Can you mute everyone?
yeah, if you folks on Zoom would mute your microphones until the Q&A portion of the meeting. If you got any questions, please put them in the chat and we'll read them at the end of the presentation for Q&A, please. So meanwhile, keep your microphones muted if you would, please. Okay, well, it's 6:30 now, and I want to welcome you all to the October meeting of the Stockton Astronomical Society. It's good to have everyone here, and it's great to have everyone on Zoom. Looking forward to a great presentation. So I'm going to quickly just turn this over to Omar, and Omar is going to make the introduction of our speaker. So here you go.
All right, good evening, everyone. My name's Omar, and I have the pleasure of introducing our speaker tonight. And that's no small task, trust me. All right, so after having retired as the chair of the Foothill College Astronomy Department, Professor Fraknoi has remained very active in the field and now teaches astronomy for the Fromm Institute of the University of San Francisco. He served for 14 years as the executive director of the Astronomical Society of the Pacific from 1978 to 1992. He serves on the board of directors for SETI, the Search for Extraterrestrial Intelligence, and he has won numerous awards, including the Innovations League's award for Innovation of the Year in 2005. He was named the 2007 Professor of the Year for the state of California by the Carnegie Endowment for Higher Education. He was given the Annenberg Foundation Prize of the American Astronomical Society, and so many more that I can't list because if I did, there would be no time for the talk. He has been a regular on local and national radio talk shows, including NPR's Science Friday, and has appeared on both local and national television, including The Today Show, CBS Morning News, and Larry King Live. Professor Fraknoi is a prolific writer, having contributed to many educational texts and was the lead author of a textbook appropriately named Astronomy, which is the most widely adopted astronomy textbook in the US. And that is available on OpenStax for free and Amazon for not free. And has also written a number of science fiction short stories that are very engaging, of which 11 have been published and can be found on his website, fraknoi.com, by following the science fiction link on the homepage. Finally, how cool is this? He has an asteroid named after him.
Yes, it is.
Asteroid 4859 is now known as asteroid Fraknoi. So, ladies and gentlemen, Professor Andrew Fraknoi.
Oh my goodness. Well, thank you for that wonderful introduction. I guess I should begin by mentioning that asteroid Fraknoi is a very boring asteroid in the main asteroid belt and is of no danger to planet Earth. That's important to get out of the way. And thank you, Stockton Astronomical Society, for inviting me to speak and tolerating this long distance way of speaking. So I'm going to go to slides, which are much more interesting to look at than I am, and then we'll start talking about black holes. And as Omar said, if you have questions, it would be good to put them into the chat. We already have 50 people on Zoom, and more are expected. So it's going to be a little bit hard to recognize people who raise their hands. So I'm putting the question into the chat, and then Omar and I can deal with them. All right, so let me now try to go to my slides. Here we go. Are they showing? Can you see them, Omar?
It's got something. I do see the slides, but at this moment, there's.
I'm sorry. Yeah, we do.
Yeah, we see the slides.
Good. All right. So this is my topic for today. I want to talk a little bit. Some people are not muted, it sounds like. So can we again ask everyone who is online to please mute during the talk? That would be a big help for us if all of you listening could just mute your audio. And that way we won't get interrupted. Thank you so much. All right, so this is my topic for tonight. I want to talk about black holes as space warps, time machines, and the sites for the gruesome deaths of stars. Um, and certainly fair to say that black holes have been a lot in popular culture. I love this cover of Time magazine, which describes our deficit, our federal deficit, as our economic black hole. And there you see our money going down into the black hole. We'll talk about that picture in a little while in a scientific way. I also discovered through the help of one of my students that there's a black hole pinball machine which you can order. I don't know what happens to the balls that disappear. Um, so let me hold on. I need to move a phone out of the room. Sorry about that. We don't usually get phone calls on the landline. So, all right. So, as I say, this is a black hole pinball machine. This is a cartoon, which I think is very appropriate. So people have seen black holes. There have been science fiction movies about black holes, but most people don't really know what black holes are. And I want to talk tonight about the basic science of black holes, and then we can get more into the science fiction and the applications of the idea. So the notion of black holes begins with gravity. The idea that there's an irresistible force that controls the universe, which is gravity, first really explained in terms of a scientific law by Isaac Newton. Um, and it's really the pull of every piece of matter in the universe on every other piece of matter. Doesn't matter what it's made of. If it's stuff, if it's made of atoms, it will have this gravitational pull. And it's something which acts over large scales and is incredibly important in astronomy. And we might ask the question, why don't bodies in space collapse under their own gravity? The matter of the Earth pulls everything downward toward the center of the Earth. Why doesn't the Earth collapse? And we know that the Earth doesn't collapse because it's solid. There is a chemical bond force which is strong enough to resist the pull of gravity. Now, if you throw your astronomy textbook off a tall building, there's nothing holding it back and it will fall as far downward as possible. But the Earth itself is structurally kept from collapsing by the fact that it's solid. But that leads to a very interesting question right away in astronomy. The sun and all stars are balls of hot gas. Why don't they collapse under their own weight, under their own gravity? There's an enormous amount of matter bound up in the sun. Just because it's in the form of gas, it's not exempt from the law of gravity. Why doesn't the sun collapse? And this idea told astronomers right away that there must be some force inside the sun which counteracts the inward pull of gravity, something pushing outward with equal force. And we now know that there are nuclear reactions going on deep inside the sun, at the hot center of the sun and of all stars, a process called nuclear fusion, the kind of nuclear reaction we get in the hydrogen bomb, which is the most potent weapon we have on Earth. And the power of fusion pushes outward and exactly balances the inward pressure, the inward pull of gravity. And as long as the sun is an active living star, and again, this is true for all stars, there is an equilibrium, a balance between gravity pushing inward and fusion energy pushing outward, and the sun doesn't collapse. During its life, it will undergo changes in size. Sometimes it'll swell up when it's adjusting to a new kind of fusion. Sometimes it'll get a little smaller again. But the general idea is that stars are in balance. But the fuel in stars, just like the fuel in our cars, doesn't last forever. And eventually, all stars will run out of working fuel. What will happen then? Well, gravity, having waited billions of years, will say, aha, it's my turn. Now there's nothing counteracting me, and I'm going to squeeze as much as I can. And a star's worth of material can squeeze quite a bit. So at the end of its life, every star will collapse under its own gravity. For stars like the sun, which is not an especially big star, for stars like the sun, it will essentially collapse until it solidifies. It's not quite a solid in the standard way. Daphne, could I ask you to mute your audio,
Oh.
please?
I'm sorry.
Um, so it's not quite a solid in the standard way, but it will collapse until it acts like a solid. It becomes a weird carbon solid, which we call a white dwarf. But what's exciting for our topic tonight is that there are stars much bigger, much more massive than the sun. And when they collapse at the end of their lives, our science tells us that they are so massive that no force we know of in the universe can stop them from collapsing forever. And forever is a long time. We really have to apply all our best knowledge to this idea and to ask what happens when a dying star collapses and collapses and collapses, and nothing can counteract that collapse. Turns out that Newton's gravity theory is inadequate to describe the situation. We needed a more sophisticated theory of gravity, which was first put forward by Albert Einstein in 1916. Here's my favorite picture of Albert Einstein. This is an Italian ad for Carlsberg beer, which says, instinct says beer, reason says Carlsberg. And Einstein is our representative of reason. So let's talk a little bit about Einstein's more sophisticated theory of gravity. It's called the general theory of relativity. And at its heart, it's a geometric theory of gravity. Right. So what the heck does that mean? So what Einstein suggested, and this is really quite something, is that you can think of gravity not just as a pull, but as a warping or distortion in the fabric of space and time. Now, you might say, I've lived in gravity all my life, and I haven't seen any warping or distortion of space and time. What's the man talking about? But Einstein replied to that challenge, which many people put forward in his time, that gravity on Earth is simply too weak. On Earth, the Newtonian, old-fashioned view of gravity is perfectly adequate to describe what happens. Only when we get to really extreme examples of gravity do we need to invoke this more sophisticated theory that gravity can be thought of as a warping or distortion of space and time. So how can we think about this? I've come up, this is not original with me, but I have an analogy that will help you. Imagine that we take all of space and make it into a rubber sheet. You know, the kind of sheet that they put under the beds in hospitals, if just in case there's an accident. Imagine you have a rubber sheet which is stretched taut on four poles, and that's going to represent space itself. And then we want to measure what happens to space as we put different amounts of gravity in it. And so we need something that can measure the sort of structure of space. In real life, it's a beam of light that helps us measure because beams of light travel in straight lines. So imagine instead of a beam of light, I have a trained ant. B.F. Skinner or somebody trained this ant to always walk in a straight line, just like light does. So we have a flat rubber sheet, which you see in the upper picture here, and I'm going to send my trained ant across, and it's going to go across in a beautiful straight line and get a piece of sugar or whatever it takes to reinforce its behavior. Now I'm going to put a grain of sand on that rubber sheet to represent a mass. What will a grain of sand do to a hospital quality rubber sheet? And I think you'll all agree, not much. Grain of sand doesn't have much weight, so it's not going to distort the sheet. The ant will go by this grain of sand and say, no big deal, and still walk in a beautiful straight line. Now I'll put a pebble on the rubber sheet. A pebble is a greater mass. What will that do to the rubber sheet? Well, not very much. If you go right where the pebble is, you might see a tiny indentation in the rubber sheet, but really nothing significant. But now let's go and get a really good heavy paperweight. The paperweight, when you put it on the rubber sheet, will have a significant effect on the geometry of the sheet. And that's what's shown on the bottom picture here. A paperweight will really distort the sheet, will really make it sag. And since ants can't fly, if we ask the ant again to go across the rubber sheet, it's going to have to follow the structure of the sheet, which is all bent by the paperweight. And the ant is going to go and describe the path seen with the red line at the bottom. Now, the deal with the ant was it gets a piece of sugar if it goes in a straight line. Ladies and gentlemen, you're the judge and the jury. In the bottom picture, did the ant go in a straight line? And you might have two schools of thought on that. One school of thought, which we might call the conservative school, might say, no, 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 that doesn't look anything like a straight line. We're not going to give the ant any sugar. But there's another school of thought, which you might call the progressive or liberal school of thought, which might say, well, wait a minute, it's not the ant's fault. It's society's fault that the ant went in this skewed, not so straight line. The ant has to travel on the rubber sheet. If the rubber sheet was bent, then the ant's path is going to be bent. You're not going to punish the ant for what is not its fault. And so you might give the ant a piece of sugar. So let's now take a look at this analogy and see what's represented by everything. The rubber sheet, remember, is space. The ant represents a beam of light. And the grain of sand was the Earth. The Earth's gravity is so little that we can't really detect much distortion in space and time. The pebble was the sun. The sun makes a very small distortion in the structure of space and time. But the paperweight was a dying star. In a dying star, the distortion in space becomes extreme, so much so that even beams of light should bend and warp their path as they get near the dying star. And this gives us a hint as to how we might tell that a dying star is there. So that's a kind of everyday analogy for Einstein's idea. And so if you have a dying star in space, of course, space is three-dimensional, it's not flat, but imagine we have a cross section through space. If you have a dying star, in its neighborhood, space, Einstein said, would be really warped, so warped that beams of light could not continue in a straight line path, but would be pulled inward. So now I want to ask my favorite question in science. Why should you believe a word of this? I mean, this is, in Einstein's time, scientists also had a lot of trouble with this. This is a really radical and novel idea. Why should I believe that space warps or bends when gravity becomes extreme? So, as always in science, we need an experiment. We make decisions in science based on experiments. And Einstein knew that this would be a tough sell. So he himself suggested this experiment. He said, wait for the next eclipse of the sun. During an eclipse, I think all of you who are astronomy fans know, the moon gets in front of the sun and the sun goes dark, and we can see stars near the sun. Einstein predicted that as beams of light from distant stars came by the sun during the eclipse and came to Earth, the stars nearest the sun will be out of place by a small amount because their light is traveling by the warped space that's near the sun. No one had ever measured what stars did when their light got near the sun because the sun's too bright. But during an eclipse, when the sun goes out, you can measure the position of the stars and see if the light from the stars comes in a straight line, which means that the stars will be in the same place as they always are, or if the beams of light going by the sun are warped in some way, which means they'll be out of place a little bit because of this warping. No one had made this measurement. In 1919, an eclipse was visible off the coast of Africa. This is a newspaper drawing from that time. A team of astronomers went from England to this island off the coast of Africa. They also went to other places in South America, but the one in this island was by far the most successful. And they measured where the stars were that were closest to the sun. And lo and behold, those stars were out of place, were out of their usual place in a star atlas by exactly the amount that Einstein's theory predicted. This actually became headline news. There was a headline in the New York Times, lights askew in the heavens. And it became one of the most dramatic proofs that this more sophisticated theory, the general theory of relativity, is the correct way to look at the behavior of gravity and what happens when light goes near strong sources of gravity. Okay, other tests have been done since. When we sent the Viking spacecraft to Mars, we knew that Mars would go behind the sun as seen from Earth. It sent a radio wave that went as close to the sun as any wave we've measured was able to go. And again, the radio wave was out of place, was bent and warped by exactly the amount that Einstein's theory predicted. This was an experiment done in 1976 and 77. We did an even better experiment with the Cassini spacecraft that went by Saturn. It again sent a message from Saturn so that the radio wave went near the sun on its way to Earth. And by gum, that radio wave was warped and out of place by exactly the amount that Einstein's theory predicted. There are many other proofs, but I think by now you get the idea. So this bizarre idea proposed by Einstein, a very imaginative genius, turns out to be the way that gravity works. And if that's true, then the stronger the gravity, the greater the warping, according to Einstein. And near a dying star, the warping becomes extreme. And the theory predicts that near a dying star, a massive dying star, the warping becomes so great, are you ready for this? That straight lines become circles. And instead of light traveling in a straight line, light will go in a circle and never get out. Now, this is a very dramatic prediction. Let me say it again. If gravity warps the fabric, the structure of space, we'll talk about time in a minute. If gravity warps the structure of space, then the greater the gravity, the greater the warping, the greater the distortion. Eventually, as a dying star collapses and becomes more and more gravitationally condensed, I like to use a technical term, squozen, right? The star will become squozen, like fresh squozen orange juice, squozen more and more as it collapses. The gravity will get stronger and stronger near its surface. So in that case, eventually the gravity becomes so strong that light, trying its best to go in a straight line, will encounter space so warped that it goes in a circle instead of a straight line. And if it goes in a circle, it will never emerge to continue its journey. And in that case, if there's a beam of light trying to get out of the star, it too will go around in a circle and never emerge. So no light from the star can reach the rest of the universe, and light from the rest of the universe is trapped to circle around the star. What color will this object be then from far away? Well, if no light emerges, it will be black. And if light can't get out, then nothing else will ever get out. So if you throw a teddy bear in, you'll never see it again. So that's like having a giant hole in space from which things don't return. And so we have dubbed these collapsed stars black holes, places where gravity gets so strong that nothing, not even light, can get out. The zone around the star where you get trapped is given a special name. We call it an event horizon. And I should tell you the story that Einstein actually didn't calculate the characteristics of a black hole from his theory. It was there ready to be calculated, but he didn't think about doing that. And it was an astronomer, physicist by the name of Schwarzschild, who actually was a German scientist who'd been sent to the front in World War I, but was so fascinated by Einstein's theory that during the evenings he would read about Einstein's work, and then he sent, as one of the last things he did because he was killed on the front, he died actually from an illness, he sent Einstein a letter calculating the characteristics of a black hole. So in his honor, we call the size of a black hole its Schwarzschild radius. Here you see Carl Schwarzschild before he passed away. The place where the black hole collapses and collapses and collapses forever is a place where our science and math breaks down because it's infinitely squozen. So we like to give that a name. We feel better when something we can't do calculations about at least has a name. So we call that the singularity. And the nice thing about the singularity is that it's deep inside the event horizon. And the event horizon is the zone where you get trapped. So once something falls into the event horizon zone, it'll never get out again. And some message from inside can't get out. And so whatever horrible properties this singularity, this infinitely squozen place has, we in the universe are protected by this event horizon through which communication is not possible. That is to say, you can fall in, but nothing can get out. The event horizon is the place where nothing, not even light, can get out. And for those of you who are interested in mathematical calculations, you can see the formula for the size of the event horizon here. That won't be on the quiz if you're not mathematically inclined, but there's the formula. And it just depends on the constant of gravity, on the speed of light squared, both of which are constant numbers, and the mass. So the size of the event horizon is proportional to, depends on, the mass that falls inside. The bigger the amount of stuff in the black hole, the bigger the zone where you get trapped, the bigger the event horizon. And this is the basic idea of black holes. From far away, the black hole has gravity just like the old star that collapsed. From far away, you don't sense any unusual gravity. It's only when you get near the black hole that the transformation of space makes this very unusual structure in which there's an event horizon surrounding a singularity. So artists have tried to portray a black hole because a black hole is three-dimensional. It's very hard to do that. But here's a nice artist trying to paint a black hole, and there's the sheet, the rubber sheet of space kind of warping in. There's a beam of light disappearing inside the black hole. There's another dying star going around the black hole. That's not a necessity. We just put in because it looks good on the painting. But that's one way of understanding a black hole visually. We're seeing a cross section of space warping, bending inward here. So I'd like to ask, what's it like to fall into a black hole? And I want to show you it's kind of a once in a lifetime experience. Let's imagine the average spaceship. Here you have the average spaceship. Of course, Star Trek fans know this is not the average spaceship. This is the legendary Starship Enterprise. But let's imagine for a moment that the Enterprise gets too close to a black hole. What color is a black hole? Black. What color is space? Black. So, of course, the gravity is enormous. So, Mr. Spock would have to be asleep at the gravity meter. But let's imagine that through a bizarre set of circumstances, the Starship Enterprise gets too close to a black hole and is pulled in. Immediately, they will be trying to send messages. And what will happen to a message? A message won't be able to get out. Because once you're inside the event horizon of a black hole, no message that you send can get out. Light can't get out, and light is the fastest thing there is. If light can't get out, radio waves can't get out. So if Lieutenant Uhura gets on the radio set, her message will come around in a circle. And nothing material like a little shuttlecraft from the Starship Enterprise will ever be able to get out. So once the Enterprise falls into a black hole, nothing they do, no message they send will ever reach the rest of the universe. Now, just in case you feel sorry for the crew of the Enterprise that it's falling into a black hole in my example, let me tell you that in real life, the crew of the Enterprise won't have a long time to feel sorry for themselves. Because as the members of the crew, as any astronaut gets near a black hole, the gravity becomes enormous. And so the gravity you feel on your feet is always a little bit heavier than the gravity you feel on your head. That's true on Earth too. Your feet are a little closer to the center of the Earth's gravity than your head is. So your feet feel a little bit more gravity than your head does, even in Newton's view. But nobody gets upset or concerned about that because, the difference on Earth between the pull on your feet and the pull on your head is completely trivial. But as you get near a black hole and gravity becomes intense and enormous, then the difference in pull between your feet and your head, if you're falling in feet first, will become enormous, will become so large that your feet will try to fall in much faster than your head. And you will begin to stretch as the gravity on your feet becomes so much greater that it's pulling intensely on your feet, much more so than on the rest of your body. Now, how stretchable is your body? As they found out during the Inquisition, human bodies are not especially stretchable. So eventually, the astronaut will be pulled into pieces as they fall into a black hole. Scientists have given this a name. they call it the spaghettification of astronauts because they will be pulled into this long stretch structure. But really, they'll just be pulled apart, first into individual body parts and then into individual smaller structures and then into individual molecules and atoms. So don't feel sorry for the Enterprise crew. They won't have a long time to feel sorry for themselves. But whatever happens to things falling in, the important thing is once things fall in, they become invisible to us. And so you might appreciate my slogan, which astronomers have popularized: what happens in the black hole stays in the black hole. The black hole cannot send messages, cannot tell us anything about what's happening inside. And so we want to ask again, why should you believe a word of this? Are there really stars which at the end of their lives collapse forever and make such incredibly bizarre structures called black holes? And what answering this question would entail is finding a dying star and measuring its characteristics. But when the star dies, a typical massive star, when it dies, we calculate that the event horizon will be about 20, 30, 40 miles in diameter. And it will be totally black. So is space. So if a dying star thousands of light years away makes a black hole that's completely black and 40 miles across, I dare you to find that 6,000 light years away. There seems to be no way of actually identifying black holes. But nature has been very kind to us. Turns out that nature often makes stars that live not by themselves, but in pairs or triplets. This is beautifully shown here in the scene from Star Wars on the planet Tatooine, where Luke Skywalker sees two suns set or rise, because these two suns are quite close to each other, and the planet Tatooine orbits both stars. This is called a binary star or a double star, and sometimes they can be quite close to each other. And if such binary stars, one of the members dies, and it becomes a black hole, the other star will keep going around it because the gravity at some distance from the star, the dying star, will be the same. And so the living star will continue to go around the dead star, the black hole. And we will, if we observe the living star, observe a star which seems to be going around like crazy, but there's nothing at the center that it's going around to see. And so astronomers have been on the lookout for exactly this situation. Some star which shows every evidence of going around in a tight circle, but absolutely nothing visible from the center of that circle. Then, and here's an artist's diagram, it may even be that the living star, especially when it swells up during its life to become what astronomers call a red giant, the living star may find some of its material pulled toward the black hole. And that may set up a kind of doom spiral, literally a doom spiral, right around the black hole. Here you see an artist trying to portray this. Here's the living star shown in yellow. Some of its material in the direction of the black hole is being pulled in. That material goes faster and faster in a kind of spiral structure right around the black hole until some of it falls into the black hole and disappears. We see some of the material being spit out in jets, but that's a separate idea we're not going to talk about tonight. But the material disappears into the black hole at the center. And so what if we could find such a structure? A living star showing evidence of going around nothing, and then this tiny spiral structure right around the black hole, outside the event horizon, so still visible to the universe. What would this doom spiral of infalling material produce? Turns out the energy of falling in would be so great, it would make X-rays. Not visible light, but X-rays. So here is the recipe for finding a black hole. Find a living star that seems to be going around nothing, and from right smack dab in the middle of the nothing, look for flickering X-rays from the doomed material before it enters the event horizon. And just such a star, just such a structure, was found in the constellation of Cygnus the Swan. It's given the name Cygnus X1, the first X-ray source found in the constellation of Cygnus. You see it circled right here. Perfectly ordinary star, which seems to have the measurable characteristics of going around and around. And smack dab in the middle of that nothing that it goes around, we see flickering X-rays coming from it. Cygnus X1 was the first structure we found that met all these characteristics, and therefore is thought to be the first confirmed black hole in the Milky Way galaxy. Again, here is an artist's painting. It doesn't quite look like that. Mr. Trippa, if you could mute your phone, that would be very nice. Thank you. So, but here's the idea. Here's the black hole. You can't see anything. It's an event horizon and it's completely black, but material from the living stars falling in, except of course the artists can't show X-rays, so they just show a kind of intense ring. But imagine that's glowing in X-rays. This discovery became so famous that a rock and roll group called Rush, in their album Farewell to Kings, actually has a song called Cygnus X1 in which they celebrate this discovery. And there's even a Marvel comic book based on the song in which the idea of the Cygnus X1 black hole is celebrated in cartoons and in song. The X-ray is her siren song, is one of the lines from that song. Since then, we found many other black holes in the Milky Way galaxy, which are also this situation of a living star seeming to go around nothing and X-rays coming from the central region. And so now we have dozens and dozens of examples of a binary star where one of the stars has become a black hole. And most astronomers, even those who were quite skeptical at the beginning, have now accepted that black holes are real, and most scientists have come therefore to accept that Einstein's much more sophisticated and much weirder theory of gravity must also be true. Well, if that's true, what about time? I mentioned that Einstein predicted that space and time would get warped. What did Einstein's theory predict about time near a black hole? And the theory is quite clear and quite simple and quite bizarre. It predicts that the stronger the gravity, the slower time itself will run. Right. What? So that Einstein said not only is the structure of space affected, but also the very movement, the very pace of time is affected. The stronger the gravity, the slower time itself will run in that neighborhood. And if you were to enter that neighborhood, you would enter a place of slowed down time. Again, you can ask, why should I believe a word of this? When Einstein proposed this theory, there were no clocks good enough to measure the slowing down of time by any gravity in our neighborhood. Because in our neighborhoods, gravity, thank goodness, is not so strong. We're not spaghettified in real life. But by 1959, atomic clocks on Earth had gotten good enough, had measured time to fine enough intervals, that we could perform an experiment to measure this. And two scientists, Pound and Repka, at Harvard in 1959 built two of the most accurate scientifically designed atomic clocks ever built. They put one at the top of the physics building at Harvard. They put another one in the bottom of the physics building at Harvard. Where was gravity stronger? Well, gravity gets stronger as we're near the center of gravity, as we're near the center of the Earth. So the clock in the basement was feeling slightly stronger gravity than the clock on the roof of the physics building. And this clock could actually measure the difference. They did the experiment, and by gum, the clock in the basement ran slower by exactly the amount Einstein had predicted. Here is the building at Harvard. You can go to the top of the tower or to the basement below ground level, and that difference was enough to measure the effect. The effect was really tiny. A clock on the Earth's surface and a clock 1 mile up would be off by 1 second after 200,000 years had passed. So this is an incredibly tiny amount of time difference. But this leads us then to the idea of a time machine, of a scientifically reasonable time machine. If you go near really strong gravity, time will really slow down. And so for if you could somehow take a trip near a black hole and then come back to Earth while you were near the black hole, you'd of course have to not get into the black hole because you'd never come back. But if you were near the black hole, time would slow down, time would run normally on Earth. And so you would be younger, let's say, than your twin on Earth when you got back because you went through slowed down time near the black hole. This is explored in a wonderful science fiction novel by Larry Niven, who was a math major at UCLA. In this novel, World Out of Time, through a bizarre series of circumstances, a spaceship is sent near a very large, very massive black hole. And when the spaceship then comes back to Earth, the Earth is 1 million years in the future from the time of the astronaut. And everything is then all about how different things are on Earth for this astronaut. But again, experiment after experiment has now confirmed that this time aspect of Einstein's theory is also correct. So this is a lot to take in. If you have not heard these ideas before and your head is now swimming, you're doing great. This is something that most people, when they first hear, really have a lot of trouble incorporating into their normal thinking. So I'm going to stop soon, but I want to now talk a little bit about other astronomical implications of this black hole idea, because this notion has transformed our view of the universe in the last few decades. Most black holes are far away from other things. And so once they've eaten everything in their neighborhood, there's no more food for them to eat. And the black hole just settles down into this existence with an event horizon, looking black, and lots of space between it and the next star. And it represents no danger to the rest of the galaxy unless you get close to it. And so most black holes can't really do much damage, even though you might see headlines in, really bad newspapers about a black hole eating Cleveland or something like that. That's not going to happen. The black holes in the real world are far away from all the other stars and are no danger, except if by some bad mistake you happen to get near them. But if black holes are in a place where there's food available, where things can fall down the black hole can then eat whatever's in its neighborhood. And the more they eat, the bigger they get. This is like the blob that ate Chicago. I don't know if you remember that movie, but the blob that ate Chicago, the more it ate, the bigger it got, the bigger it got, the more it could eat, the more it could eat, the bigger it got. And pretty soon it was the blob that ate Chicago. But this is only true if the black hole is located in a neighborhood where there are things close enough, gas, dust, planets, stars, close enough to it so they can fall near enough to be sucked in, to be pulled by the much stronger gravity that only is strong near the black hole. But we know that there are places like this at the centers of all galaxies. Our Milky Way galaxy and all galaxies of stars have a central region which is much more crowded than the suburban part of the Milky Way galaxy where we live. So nothing we observe in our neighborhood is really an indicator of what it's like at the very core of the Milky Way galaxy and at the core of other galaxies. There we believe monster black holes become possible. Um, and so here is a typical galaxy. We can't see the Milky Way, we're in the middle of it. But if we could see the Milky Way galaxy of billions of stars and lots of gas and dust from far away, this is what it might look like. We're out here in one of the outer spiral arms of stars and dust. But at the center, things are so crowded that it all blends together into an enormous glowing ball. And the same is true at the center of our own Milky Way, too. And so in that central region, can people please mute? Mr. Ransford, can you mute your audio, please? Everybody who's got audio, please mute. So at the center of a galaxy, at the center of our Milky Way, things are so crowded that if a black hole forms, as always will happen because big stars exist everywhere and they die, then that black hole can eat and grow. And the more it eats, the bigger the event horizon, the bigger the event horizon, the more it can eat, the more it can eat, the more can fall in, etc. And so the black holes get bigger and bigger and bigger. And in our own Milky Way, we have now become so good at observing the crowded center, not so much in light, because the light all kind of looks like a glowing ball, but in infrared light, we can actually see individual stars going around the very center of the Milky Way. This is a diagram made by a group at UCLA led by Andrea Getz. And they have been able to track the motion of stars whirling around the center of the Milky Way. And stars generally have a stately motion. So if they whirl around, there must be a lot of gravity pulling them. And from the motion of these stars, Andrea Getz's group and another group has been able to calculate how much gravity must there be at the center of the Milky Way that is pulling these stars around so quickly. And when she did the calculations, she had to gasp, because what it showed was that at the very center of our galaxy, there was an invisible region with enough mass to make 4 million suns. 4 million suns are all inside this region, which to the best of our ability to tell looks black at the center, but it pulls stars around it really fast. And so we now believe that there is a black hole at the center of our Milky Way galaxy, which has eaten the equivalent of 4 million suns. The observations became so good that in 2020, Andrea Getz, whom you see on the right, and the leader of the German group, Reinhard Genzel, received the Nobel Prize in physics. They shared it with a black hole theorist. But the Nobel Committee thought that this was such a good observation and so convincing about the black hole that this has now established that the Milky Way has a black hole 4 million times the mass of the sun. But we now know that the black hole in the Milky Way is a baby compared to some other galaxies. There are other galaxies where the center glows with X-rays, just like Cygnus X1. And I'm not going to go into all the details, but it now turns out that many galaxies have black holes. This particular galaxy, which has the catalog number NGC 3115, turns out to have a black hole which is somewhere between 2 and 3 billion suns. Not million, but 1,000 million billion. 2 to 3 billion stars like the sun are trapped in the central black hole of this galaxy. And many new surveys and new instruments have shown us that almost all significant major galaxies seem to have a supermassive black hole like this at their center. And this is really quite a remarkable observation. And it shows us that this small notion that kind of came out of Einstein thinking about the nature of space and time and gravity. This bizarre notion that space can warp and time can slow down now has quite a large scale application in these supermassive black holes. Near these supermassive black holes, time would slow down enormously. Even before you fell in, you would see tremendous slowing down of time. And that's how in the science fiction novel I showed you, the protagonist could come out 5 million years in the future because the slowing down of time is proportional to the strength of gravity. And so we have in these situations tremendous applications of Einstein's theory. Well, I hope I've been able to show you that there is a lot to be learned about black holes. There are many more things I could tell you about, but I want to go actually to the last slide and finish up with my bumper sticker. And I hope you'll agree that black holes are out of sight. Thank you very much. All right, I'll stop sharing. Thank you, everyone. And Omar, I don't know whether you want to say anything or we should go to questions.
Yes, we can go to questions, and we want to start here in the room. Is there anybody in the room that would like to ask a question? Getting a lot of blank stares? No, here we go. Here's Doug.
So I had heard that Einstein really didn't like the idea of black holes. How long did it take for him to come to the point where he realized that they do exist?
I don't think you heard right.
Okay.
Einstein had no problem with black holes. So the idea that this is often told about is quantum mechanics.
Ah,
Einstein's work
yes, I know.
predicted in some way quantum mechanics, and he really didn't like quantum mechanics. And that's a different story. But no, Einstein immediately took Schwarzschild's paper. Remember, Schwarzschild was at the
Yeah.
front, and he made sure that Schwarzschild's paper was published.
Okay.
And he said, this is a great application of my theory. Again, whoever it is, please mute you. Thank you. So he was he didn't have the word black hole. Black hole was first invented as a term in the late 60s and 1970s. But the notion of Schwarzschild solving this for this kind of a situation was fine with Einstein.
Yeah. Okay. Thanks.
All right.
Andrew, hi, Pat Lehman. We met last night, so
Yes,
thank you
hello.
again for being here tonight. You know, I'm trying to get my head wrapped around some of what you shared, and if I think about light spiraling in onto a black hole, does it spiral in indefinitely, or does that energy ultimately get consumed by the black hole in some way? Or I know this is all theoretical, but do we have any perspective on that?
Yeah, this is a great question, and this is the kind of thing that graduate students get PhDs on. Looking at how do we apply Einstein's equations and our best knowledge of light to an actual situation. So some of the light gets trapped around the black hole in what we call a photon sphere. This is the structure around the black hole is more complicated than in the simple talk I was able to illustrate. But some of the energy will fall into the black hole. And matter and energy, which are equivalent according to Einstein's other theory of relativity, will then simply spiral inward toward this place called the singularity, where mass and energy become infinitely concentrated. So, one of the things I didn't have time to talk about is that Einstein was really bothered by this. Wait a minute. Where does it go? I think that's what your question implies. Where does the black hole stuff go? And the equations break down. Whenever the equations predict that something gets infinitely squozen or infinitely anything, those equations break down. And so when the equations break down, we don't know what's happening. And people have for a long time been trying to figure out what might be the right theory so that the equations don't break down at the singularity. And people have some suggestions. But Einstein himself wrote a paper with a colleague called Rosen, in which he proposed something which has now become known as the Einstein-Rosen bridge. And he suggested that the black hole material could make a kind of pathway to elsewhere or elsewhen in the universe. What? So that the material of the black hole, when it's infinitely squozen, represents a kind of path through space and time to somewhere else. Now, nobody paid much attention to this until someone came up with a sexy name. The name they came up with is wormhole. The wormhole is the same idea in an apple. If you want to go from another place on the apple surface, you have to go around the whole surface. But if you're a worm, you can eat your way much more directly from one side of the apple to the other. So they called this kind of path through another place or time a wormhole. And since then, this has become a darling of science fiction and of science. People have talked about this when Carl Sagan wrote his novel Contact. He needed a wormhole for Ellie Arroway or Jodie Foster to travel through. And he went actually to the biggest black hole theorist in the world, Kip Thorne, and said, Kip, I need you to come up with a realistic wormhole right away because I need it for my novel. And Kip told his graduate students about this. And one of the graduate students wrote a PhD thesis where he did the math for the wormhole. And so then Kip called Carl Sagan, said, it's okay, you can use it in your novel. One of my graduate students solved some of the math. So now in many science fiction stories, you have this idea of a wormhole, which gets you to another place in the universe without having to worry about the speed of light. And in the movie Interstellar, for which the plot was written by Kip Thorne, that's that physicist, we have a wormhole playing a big role in the movie, making the plot of Interstellar possible. So sorry, that was a very long answer, but you asked such an interesting question. I wanted to get you to the current thinking.
I'll follow up with a tongue in cheek, and thinking about the spaghettification of the astronaut, because time then warps. Is it correct to think that they will move at beyond the speed of light, but their experience slows?
Yes.
So and it actually kind of leads into just the wormhole. The speed in the wormhole then has warped somehow, and I'll have to go watch the movies to see what the real theoretical answer is. But thank you.
I can't resist saying that This is the basis of one of my science fiction stories that uh, Omar so kindly mentioned at the beginning. I've been trying to write astronomically reasonable science fiction stories, and I thought I had to write something with this idea. And I wrote a story called Slow Time Station, in which the protagonist has a very bad breakup with his girlfriend, and he wants to forget her, and he wants the world to forget her, and he wants to live at a time when no one has heard of her. So he goes to a black hole where you can pay to be near the black hole, have time slow down, and then when he comes out, everybody would have forgotten about his this doomed love affair girlfriend. Something funny happens as a result of this, but I'll let you read the story. As Omar said, if you want to read my stories, they are all available now free on the web. And if you go to my website, fraknoi.com, you can read the science fiction stories, including this Slow Time Station. So that was a shameless plug. Shall we take some questions from the web audience now?
Yes. Eric, if you can scroll to the top, there was a discussion that started with a comment by R. Marr, and the comment was, I assume the reason the gravity is greater for a dying star is that its diameter is a lot less and the light beam can get closer to the center of the star where the gravity is a lot greater.
Yes, that's right. So gravity depends on two things. Even in the Newton view that we all learned in high school, gravity depends on two things: how much stuff is being pulled and how close you are to the center of gravity. And the closer you are to the center of gravity, the stronger the gravity you feel for the same amount of mass. So as a dying star collapses, you have the same amount of mass, but squeezed into a smaller and smaller ball. And therefore, the edge of that ball is closer to the center of gravity. So the same amount of mass is squeezed into a smaller radius. And that means gravity goes up and up and up as you ride that edge of the star inward and inward and inward. So you're quite right.
Further down in the chat, Cat Gates says, I'm curious as to how the event horizon works. That is, I'm curious as to why the extreme effects of the black hole's gravity is limited to the event horizon. I wonder why the pull of the black hole's gravity is not distributed across space-time.
Yes, so it is. You're absolutely right that the event horizon is a limit to the action of the black hole. So you're absolutely right. The spaghettification, for example, starts way above the event horizon. If you're falling toward a black hole, you can be quite a distance above the black hole's event horizon and already begin to feel this greater pull on your feet and start to be very uncomfortable. But at the event horizon, it's where you are trapped. Not just you, but light and everything is trapped. So the effects are detectable much further out. Not much further out, because really far away, it's just like the gravity of the old star. But at the event horizon is the extreme limit. Once you're inside the event horizon, you'll never get out. You'll never be able to communicate. It's where the edge of the black hole is really thought to be.
Okay, we have another question here. How do they know how massive a supermassive black hole is in a faraway galaxy?
Great question. This is the kind of question I always encourage my students. Why should I believe you, right? How do you know from 100 million light years away how massive a black hole is? And there are several answers. Let me just suggest one that's relatively simple, which is we can play the same game that got Andrea Ghez the Nobel Prize. What we can do is we can watch a distant galaxy with a really good telescope like the Hubble or the James Webb and try to see near the center of the galaxy moving things around the black hole. Now, sometimes that's not individual stars, sometimes that's a large mass of raw material, sometimes it can be a kind of X-ray glow. But because motion is something we can tell in the spectrum, when we take the light and spread it out into the spectrum, we have a way of measuring the motion of whatever's giving off that light. We can measure the motion of things around the black hole very nicely, even when we don't make out a lot of detail. And so by watching what the motions are near the center of those distant galaxies, we get a sense of how quickly these things are being pulled around. And just simple gravity calculations tells you that the rate at which things are being pulled around is proportional to the matter inside the mass. And that's what tells us that there are 3 billion or 20 billion times the mass of the sun. I think the new record is 66 billion. The largest black hole is 66 billion times the mass of the sun. And that just boggles my mind.
The whole room here just kind of went, All right, we got another question from Sabrina. If one of two binary stars of the same size becomes a black hole, why would the black hole rip the other star apart?
Right. So this is an excellent question. They're not the same size. It turns out that the life story of stars is different depending on how much mass a star has. Low mass stars, little stars, live very slowly. They do everything over billions of years. And the more mass a star has, it turns out the hotter it is, and the more quickly it goes through all the stages of its life, using up its fuel because it's super hot. And so massive stars live a very short time compared to regular stars like the sun. So in a binary star situation, if they're the same mass, they're going to live at the same pace, and one won't become a black hole significantly before the other, or neither may become black holes. So you need an unequal binary star, one in which one star is really massive, the other star is kind of boring and regular, and then the massive star becomes the black hole, and the other star goes around it, and when the other star swells up, and its outer radius gets nearer the black hole, then material is ripped off the living star and falls into the black hole, which formed much earlier. So I hope that answers the question.
Okay, I had just wanted to ask if we could revisit the idea of gravitational waves that are detectable when black holes collide. If you can refresh our memory on what that is and how that happens.
I didn't say a word about that.
No,
So
you
thank you
didn't.
for saying refreshing our memory. That's a whole other topic. I mean, I could give you another hour on that whole thing. So how do I do this? Let me do it in my shortest way possible. Another prediction that comes out of Einstein's theory, general theory of relativity, is that when gravitational situations are seriously disturbed, when there's some redistribution of how matter exists in space, not only will space warp differently, but that redistribution of the structure of matter in space will produce a set of waves. And we call them gravitational waves or gravity waves. When Einstein predicted this, because the waves are much weaker than light, there was no way to prove this. People said, nice idea, Albert, but what you've predicted is such a weak phenomenon, we'll never know the answer to that. And Einstein kind of resigned himself that, yeah, you're right, these waves are so weak, there's no technology I can think of that would prove their existence. But physicists and astronomers are a heady lot. And they've been thinking to themselves, how can we build a wave detector that will pick up these incredibly weak waves? And one of the people thinking about this was Kip Thorne, whom I mentioned, the black hole expert. And he and Rainer Weiss at MIT came up with this amazing, huge device on two sides of the United States called LIGO, where they use laser light and a phenomenon that measures the timing of lasers very precisely. And they came up with something that could actually measure the distortion of space by a gravitational wave, where the distortion in space, the change in the structure of space, is less than the size of an atom. And yet, with lasers, they can measure this distortion. And a few years ago, the advanced version of LIGO measured the first gravitational wave. Where did it come from? From a really big redistribution of matter, two black holes eating each other for lunch. When two black holes collide, they eat each other, they redistribute space and time around them, and that produces enormous waves, very weak, but a lot of them and large changes. And the LIGO detector was able to detect the change in the structure of space, the wave that came from that collision of black holes. So this was sensational. Weiss and Thorne got the Nobel Prize for designing this equipment. And since then, we've had dozens and dozens of large black holes eating each other for lunch, producing gravity waves big enough for LIGO to pick up. So this is a whole nother way of showing that black holes exist, because they now produce measurable gravity waves. We live in an amazing times. I never thought in my lifetime I would see gravity waves proven, but lo and behold, we did it. So thanks for asking about that.
Oh, and thank you for that explanation. We're now at the bottom of the chat, and there was a quick discussion for the question from Val. Do black holes ever spit anything out like debris, or is gravity just that strong that it is not possible?
Oh, this is, again, could be another hour lecture, but let me do a very quick run through. No, strictly speaking, once matter falls into a black hole, nothing can get out, and nothing has been seen or understood to violate that. But then there's the accretion disk, this zone, this whirlpool of infalling material outside the event horizon. That can be quite a powerful zone, with material whirling and swirling around, fighting other pieces of material who can die first inside the event horizon. And so in that swirling disk, you can sometimes get to what we like to call an overfed situation. It's like your grandchild eating in an all-you-can-eat buffet, and they eat so fast that matter comes spitting out of the side of their mouth because they're trying to eat all this food as quickly as possible. Terrible analogy, but something along those lines can happen in the accretion disk of a black hole. And so material can actually be spit out in opposite and perpendicular directions from the accretion disk. And these would be jets of spit out material, not from the black hole, but from the zone around it. And such jets have been observed around many supermassive black holes. So the accretion disk can spit things out, not the black hole.
All right, thank you so much. That reaches the bottom of the chat and all of the questions in the room. So I believe we've reached the end.
Well, thank you very much for putting up with my jokes, and I hope I've been able to show you an interesting part of astronomy tonight.
Absolutely. We really enjoyed it. Thank you so much.
All right.
All right, now the club has a few more things that we're going to take care of. So thank you and good night, everyone.
Take care.
Tim. Yeah. That's you.
Wow, that was wonderful. I, for some reason, have a craving for spaghetti now. Get up and stretch a little bit. I know these chairs are not very comfortable, and help yourself to some refreshments over there. We're going to transition to our announcements for the club. You folks on Zoom are welcome to stay and listen in, participate if you like. I'm going to go to our announcements for the kind of a 2-month look ahead here. So Eric, tell me when you're ready to display that on Zoom. Have you guys been watching Eric over here? He's working overtime. And he had a problem earlier. He overcame it. He's just working really hard. Thank you, Eric, for everything. Okay, we're ready. So here we go. October coming up, the Highway 4 Star Party. That's this Saturday. The weather looks like it's going to be good, right? So we'd probably either go to Highway 4 or our site at Campo Seco. Look at the Google chat for people that are going to and where they're going. And then the following Saturday, 2 events you get to choose from. The High Altitude Star Party and
At the time that I got on, he was at like 79, but some people are falling off, so it's probably fluctuated.
So either the High Altitude Star Party or this Girl Scout Camp Star Party. And Doug, tell us, is that going to be out at Oak Grove?
No, that one is down near Livingston. Irby, our young astronomer, is part of this thing. She would like some of us to come down there. I have volunteered to drive down there. Somebody is willing to go down there with me. I will do the drive.
Are they meeting in a park?
It is, the Camp McConnell is where it's at. It's supposed to be a fairly dark site. I will bring a telescope for Irby, and it's her Girl Scout group is having this camp out down there. So like I said, I would really appreciate if I can get another person to help me out with, because I don't know how many kids are gonna be down there.
Right.
It's just
Okay, good.
then we're gonna need another scope.
We're good. Well, again, look at the email blasts in the Google chat. Doug will probably be issuing reminders for volunteers for that Girl Scout Star Party. Following up on October 25th, we're back out at Oak Grove Park for Astronomy in the Park. Should be a good turnout if the weather's nice that time. And then October 29th, we have a request from the George Kelly Elementary School to hold a star party at their school in Tracy.
So volunteers for that as well.
We need volunteers and scopes for that.
And
So,
October 25, Astronomy in the Park. I'd like everybody that comes to the park to come in a little early, like 5:30 or so, or 5 o'clock, and head to the Nature Center and go through the Nature Center. We have a new county parks administrator. She will be there. We want to show her what we do.
very good.
Okay, so let's go out and pump the
Okay.
numbers up for the Nature Center.
Okay, October 25th, come early to Astronomy in the Park about 5 o'clock.
Go over to the Nature Center.
Go to the Nature Center and,
And head back out, set up your stove,
okay, sounds good.
bring kids, the grandkids.
Excellent. Sounds like a good time. Speaking of good times, November 7th, we've got a big kind of to do. This November 7th meeting is not on your calendar yet, but take note. This is the presenting of the Cosmic Dawn movie at the University of the Pacific, the biology lecture hall. We've secured a location with much better comfortable seating than this place to show the movie. We're actually going to be celebrating our 75th anniversary. The SAS was founded in November of 1950. More on that in just a moment. And it's going to be a joint meeting with the Sacramento Club. There's a reason for that. More on that in just a moment. So again, November 7th, we'll be sending out notices and more information, but it's in the evening, I think 5:30 p.m. over at UOP. So I'm really interested in watching this documentary on the creation and launching of the James Webb Space Telescope, this NASA Cosmic Dawn movie.
So,
So,
do you know if that lecture hall has a room number?
has a what?
Do you know if it has a room number, that lecture hall?
I'm not sure the actual room number, but you walk in the front doors and you're there in the lobby, and nice big like a theater seating. So it should be a good time. Should be a really good time. Okay, November 13th, we're back here for our general meeting and our anniversary party. And I mean party. We're going to have cake and ice cream and cider or champagne, whatever you like to drink. Remember, this November 13th, I want everybody to wear their SAS shirts, whatever t-shirt you have. Doug's got his on, Casey's got hers on tonight. Whatever version of SAS shirt you've ever had, wear it that night. We're going to celebrate our anniversary. We're going to have part 2 of the storied past of the SAS. We're going to have more interviews and more members describing their experiences with in the history of SAS. And we're having our executive committee elections that night, as we do every year in November. So that's the November 13th meeting. November 15th, we're back out at the low altitude sites, Highway 4. November 22nd, high altitude star party. And Doug, I don't know, did I miss a astronomy in the park for November, or did we not schedule one?
That's the one Saturday after Thanksgiving, and we decided
Okay.
not gonna happen. Same thing with December. Saturday after.
Okay, we had
Christmas.
2 months off from astronomy in the park because we're going to be opening Christmas gifts and eating turkey. Okay, that's what we're doing.
So wiped out from eating so much turkey that we just can't possibly.
Okay. Excellent. Okay, everybody got the announcements? Any questions? Good. And then I told you that the November 7th meeting was kind of a special meeting with the SAS. And so, Eric, if you go to the next slide, please, I'll explain why this is. Okay, so you all know that the club was founded in November of 1950. Well, in September of 1951, Dr. Custer wrote an article for a publication called the Griffith Observer, published by the Griffith Observatory. In there, he goes back and he recollects and describes how the club was founded. So in this article, and I can share this article with anybody would like it, let me know. I'll email this to you. We've got it in PDF. And I'm going to read this because it's why we're meeting with the Sacramento Club, because you'll see here that about 60 people attended the first meeting, and it was at Dr. Custer's house. He invited the Sacramento Club, and they came down, brought their telescopes, and this is a photo of the telescopes. You've seen this before. And well, his big Springfield scope is in the back. They came down and they shared their telescopes, and they had a little dinner presentation. And so the very next month in December, the first regular meeting of the society was held at Stockton College on Monday evening, the 13th of November. Well, we're not meeting on the 13th, we're meeting on the 7th with the Sacramento Club again. So it's like a recreation, this kind of cosmic coincidence, or just maybe the cosmic chaos that's created this. So we're meeting at the biology lecture hall, which if you know your geography of Stockton and the history of UOP and Stockton College, you know that that biology lecture hall is right where the meeting was held when they met at Stockton College. So see how the universe works? Huh?
Okay.
So that's why it's kind of a special meeting. So hopefully everybody will come out. We've got plenty of seating. We're going to invite, like I said, the Sacramento Club, it's a Friday evening. As many folks from there will come down. We're going to invite the Sierra Club, the STEM department here at San Joaquin County Office of Ed, and the staff and faculty at University of Pacific in chemistry and physics.
What time is it gonna start?
I think we're starting at 5:30. We're still dialing in the details. Doug, we should invite the physics and computer science club from Delta College,
Yep.
our partners there at Delta. So should be a good time. Okay, Eric, if you'd go to the next slide then, please.
Can you send a campus map showing where that lecture hall is?
I will do that, Dina. It'll be in the announcements, certainly.
Thank you.
I hope you can come. So in the slide for the announcements, I didn't talk about this, but did you see the photo of the comet? So this is the astronomy picture of the day from today, and it's Comet Lemon. And let me just read to you, Comet Lemon, I believe that's how you pronounce it, is brightening and moving into the morning northern skies. Besides Comet Swan 225b and Comet Atlas, Comet Lemon is now the third comet currently visible with binoculars and on long camera exposures. So get up early in the morning and hopefully we're going to start being able to see this. Comet Lemon was discovered early this year and is still headed into the inner solar system. And the comet will round the sun on November 8th. So that's its apogee. But first, it will pass its nearest to the Earth at about half an EU, half the Earth-Sun distance on October 21st. So October 21st is going to be the closest, and it's visible in the morning sky. Although the brightness of comets are notoriously hard to predict, optimistic estimates have Comet Lemon then becoming visible to the unaided eye. So the comet should be best seen in pre-dawn skies until mid-October, when it also becomes visible in evening skies. And this featured image showing the comet split and the rapidly changing ion tail was taken in Texas late last week. So it's visible through astrophotography right now. It's in Gemini, right near Castor and Pollux. So it should be easy to find. If it's, I think it's like magnitude 11 now or something. So if it brightens, they're expecting it to get down to like magnitude 6 or 7. So get up early, and maybe we should even have a star party. We can go out to the dark sky site. So
Pat actually took this. Want to talk about this, Pat?
Sure. Because I'm aging, I was up at 3 o'clock this morning. And so I grabbed my dwarf and I took this picture from my backyard. So that's the same comet, Comet Lemon. That was an hour and 37-minute exposure. So you see that you can actually see the movement over the course of that hour and a half for the comet itself. It is in Stellarium, so that's that little side panel. So you could find it and track it there. It was visible with my binoculars. Got a pair of 1570s, but you had to know where to look for it, and you could see a little fuzzy element there. And then, yeah, it shifts, at least if I was looking at that correctly, as of the 14th, it'll shift into nighttime and then rise and drop off again through the November 10th. So we should get a better view. And if you noticed, it was, the moon was up tonight, last night. So I think I probably, if I was in a dark spot, would have gotten a better image out of this.
yeah.
But yep, I took a swing. In NASA, of course, made me look bad with their picture. Yeah.
Okay, we got a new object to image. So break out your gear and get up early in the morning. Thanks, Pat. Next slide, Eric. Okay, our new moon challenge for September, the new moon, the sliver moon that we're going for, the new moon was on September 21st at 1:54 p.m. So there was not going to be any chance we could see it that evening of September 21st. So it looks like Casey, you got it the earliest on September 23rd.
Oh, okay.
That's the date you sent it to me. So I assume that was about the time you got it. So nice shot. There it is over on the far right. And Casey, you got a good silhouette of Mont Diablo in the background. Like that. Ray caught it on the 25th up in Elk Grove. And I was a day later, I was traveling through eastern Idaho, and I caught it at 7:20 p.m. there in the out on the plains of Idaho. So
Were you parked or were you still driving when you took it?
there's the rearview mirror. I didn't slow down at all. It's a movie picture. So, and Rich, you caught it also?
I did, but
Okay, you get credit for it.
okay.
Okay. So, I think we're doing pretty good. A few of us have got it every month since about February. So our goal is to get 12 consecutive months of the sliver moon. But we're coming into the winter time, and that's going to be tough. So it's a lot of fun. Next one is October 21st, coming up 5:25 a.m. So will we be able to see it the evening of the 21st? Maybe. Yeah. Okay. Next slide, Eric. And Eric, why don't you talk about this?
I've recently been including in the newsletter a target of the month, just to act as a sort of challenge. Challenge to everybody. This is the Bowtie Nebula. It's in the constellation of Cepheus. Magnitude 11.6. So it's not something you're going to be able to see naked eye or anything like that. You're going to definitely need to use a scope. And it's quite small. It's only 38 by 35 arc seconds. So I definitely not even in binoculars. You're going to go into scope for this one. But these are just challenges to the club to try and see it either visually or image it with a camera if you can, and let us know if you're successful. That's it.
Excellent. Thanks for posting those, Eric. And I've got to try to get that. That should be doable. Okay, next slide, please. It's 8:05. We're here till 8:30. So I think we've got time to run this. I've got a short video. I thought it was interesting. We've heard of the Drake equation, and Dr. Carl Sagan, although it's a little bit old and dated, it's still perfectly relevant.
One of the big questions.
Here we go.
Advanced civilizations.
I'm sorry, I don't think I have shared this properly to share the audio. So let me stop sharing and reshare. Give me a second.
Okay. It's just a short video. It's about 7 minutes long.
How many of us had those turtlenecks and that hair? I was there.
I'm sorry, I'm having trouble here.
Once upon a time, I had the hair. It was thin, but I had the hair.
This is blocking me. Give me a second. There we go. I think we're good to go here. Let me lower the volume just a tad bit.
This is one of the great questions. How many advanced civilizations capable, at least of radio astronomy, are there in the Milky Way galaxy? Let's call the number of such civilizations by the capital letter N. It's a number. It depends on many things. It depends on the total number of stars in the Milky Way. Let's call that N sub star. It depends on the fraction of stars that have planets. Let's call that F sub P. It depends on the average number of planets in a given solar system that are ecologically suitable for life. Let's call that N sub E. Depends on the fraction of suitable planets in which life actually arises. Call that F sub L. Depends on the fraction of inhabited planets on which intelligence emerges. Let's call that F sub I. And on the fraction of those planets in which the intelligent beings evolve a technical communicative civilization, call that F sub C. Finally, it depends on the fraction of a planet's lifetime that's graced by a technical civilization. Call that F sub L. If we multiply all these numbers together, we've estimated capital N, the number of civilizations. This equation, due mainly to Frank Drake of Cornell, is only a sentence. The verb is equals. So let's try to go through the program of this equation. By carefully counting the number of stars in small but representative regions of the sky, we find that the total number of stars in the Milky Way is about 400 billion. It's a lot of stars. What about planets? Well, in studies of double stars and investigations of the motions of nearby stars, and in many theoretical studies, we get a strong hint that many, perhaps even most stars, are accompanied by planets. So let's take F sub P, the fraction of stars that have planets, as a quarter. Then the total number of planetary systems in the galaxy is 400 billion times a quarter, or 100 billion. We'll write down our running totals in red. Now, if each system were to have, say, 10 planets, as ours does, there would be 100 billion times 10, or 1 trillion worlds in the galaxy, a vast arena for the cosmic drama. In our own solar system, there are several bodies that might be suitable for life of some sort. There's the Earth, of course, but there are possibilities for Mars, for Titan, perhaps for Jupiter. If other systems are similar, there may be many suitable worlds per system, but to be conservative, let's choose N sub E equal 2. 2 worlds suitable for life per system. Then the number of planets in the galaxy that is suitable for life would be 100 billion times 2, or 200 billion. Now, what about life? Under very general cosmic conditions, the molecules of life are readily made. They spontaneously self-assemble. It's conceivable that there might be some impediment, like some difficulty in the origin of the genetic code, say, although I think that's very unlikely given billions of years for evolution. On the Earth, life arose very fast after the planet was formed. So let's choose F sub L, the fraction of suitable worlds in which life does arise, as a half. In that case, the total number of planets in the Milky Way in which life has arisen once is 100 billion times 2 times a half, or again, 100 billion. 100 billion inhabited worlds. Now, the estimates get tougher. Many individually unlikely events had to occur for our species and our technology to emerge. On the other hand, there might be many different roads to high technology. Some scientists think that the path from trilobites to radio telescopes, or the equivalent, goes like a shot in all planetary systems. Other scientists disagree. Let's take some middle ground and choose F sub I as 1/10 and F sub C as also 1/10, meaning that only 1%, 1/10 times 1/10, of inhabited planets eventually produce a technical civilization. If we were to multiply all these factors together, we would find 100 billion times 1/10 times 1/10, or 1 billion planets on which civilizations have arisen at least once. Now, what percentage of the lifetime of a planet is marked by a technical civilization? The Earth has harbored a civilization capable of radio astronomy only for a few decades, the last few decades, out of a lifetime of a few billion years. It's hardly out of the question that we might destroy ourselves tomorrow. If that's a typical case, then F sub big L would be a few decades divided by a few billion years, or 100 millionth, a very small number. And then big N would be a billion times 100 millionth, or N maybe just 10 civilizations, a tiny smattering, a pitiful few technological civilizations in the galaxy. But civilizations then might take billions of years of tortuous evolution to arise and then snuff themselves out in an instant of unforgivable neglect. If this is a typical case, there may be few others, maybe nobody else at all for us to talk to. But consider the alternative, that occasionally civilizations learn to live with high technology and survive for geological or stellar evolutionary timescales. If only 1% of civilizations can survive technological adolescence, then F sub big L would be not 100 millionth, but only 100th. And then the number of civilizations would be a billion times 100th. The number of civilizations in the galaxy then would be measured in the millions. Millions of technical civilizations.
That's it.
He didn't answer the question. He gave you a range between 10 and millions. He made a lot of assumptions for us of those factors. But I guess that's how he resulted in a range. So I don't know. I just was interested in how the Drake equation worked. And when you ran the numbers, what would happen? He did it for us. What do you think? Pardon me? A lot of space out there? Right.
Let's see how long we're able to survive.
Right. That last factor, he said, is how long of the planet's existence technology was, our civilization was going to survive. Right. Right. And back then, he always seems like he took a very negative stance, but this was during the height of the Cold War, the proliferation of nuclear arms. Not so much, I think we have that under control now, but probably to a lesser degree than what it was at that time, a threat. Yeah. Yeah, so maybe it would be closer to 1 million. So anyway, just food for thought. I thought it was interesting. So, Eric, I think I've got one more slide. Yep. Who has the Astro word puzzle that was in the newsletter? Okay, Eric's got it. Casey, I know you've got it. You had it last month. Okay, I just did it. Pat, you had it last month too, didn't you? You just did it?
Yeah, I did last.
Okay, anybody else? Okay. Casey, tell us this deep, deep message that is embedded in this puzzle.
What goes up must come.
What goes up must come down. That is, Jeff must have stayed up late studying Isaac Newton's theory of gravity, right? Sure. They went up and they've never come down, right? Okay, so if you completed the Astroword puzzle, your reward is a SAS sticker, another one. I've got to come up with some better prizes, I think. And that's kind of a wrap on tonight's meeting. Anybody else have anything to add? Comments, questions? Pat?
Just a little side note. So last night I went to the talk that was offered by Andrew Fraknoi at Foothill College. that it was actually given by, I went in person. It was given by a gentleman, Dr. Stephen Kahn, who's actually a professor at Berkeley right now, but he was the project manager for the Vera Rubin Observatory. So he spent 20 years planning and having that built. The talk itself, and I'll send out the link. These talks that they offer are available on YouTube a couple of days after. So this one should come up. Fascinating to see what they're doing with Vera Rubin. I know we talked about it a little bit, but give you a little bit of a data point. In each year of the 10-year of survey, they will generate more data on astronomy than we have generated in history to date. They had to create new technologies actually for collecting the amount of information, and they're developing the ways of analysis because the expectation is they will discover or they'll map 20 billion galaxies and 10 billion or 17 billion stars. So they're actually trying to figure out right now, once you have all this data, how do you consume it? Who do you give it to? So they're working through the models for that, but it's an hour and a half talk or roughly that. Fascinating talk and worth at least watching as much of it as you choose to. But yeah, I made the drive down there, which just about killed me, but enjoyed it. So
Excellent.
it's at Los Altos. Yeah. So it's a hall, but and all of the talks that they've given over the years are on their YouTube channel. So there's a lot of really, really good. I've watched probably 6 or 7 of them, but worth.
So how many galaxies did you say the Vera Rubin telescope is expected to find?
20 billion galaxies.
20 billion.
And 17 billion stars. And their real focus, the real objective, when we had, you're probably aware, Vera Rubin was in the forefront of investigating dark matter. So their 4 key objectives are to actually add more data and knowledge behind dark matter, dark energy, and then to map the Milky Way, and then really because of the way the survey runs, it's to identify changing objects, either that moved, so an asteroid or a comet that moved, or something that changed in brightness, so a supernova. And their real purpose is to do this survey every 3 nights. They survey the same region of the sky, map what's changing, and then try to get the information out so observatories then can go focus on that. So they're not trying to do a deep dive analysis. They're trying to identify spots or objects to go look at. So cool talk though.
Excellent. Well, with 20 billion galaxies, they're going to need help analyzing those. So I think if we divvy them up, we can get through a bunch of them ourselves, right? Yeah.
And that really is, they're talking about how you crowdsource the analysis. So they were saying we could give everybody two galaxies and a star to look at, but they're really trying to develop new AI technologies to help investigate quicker. One of the fascinating things is
nobody will trust the results then.
Right. The one real fascinating data point is, so they're taking 15-second images. Their objective is within 60 seconds after the shutter closes to have that image downloaded to their local data center and then pushed to the Slack data center that's in the Bay Area. So within a minute, they're looking to have the information that they collected available for consumption somewhere.
In the public domain.
Yeah.
60 seconds later.
Yeah. So they haven't proven that yet. And there's some first light images and data that, like we shared before, that
Yeah.
one piece of video.
Yeah.
But they really go live in November to start the sky surveys.
Okay. Good. Excellent. Thanks for that, Pat. So, Omar, thank you very much for setting up the speaker tonight and conducting that presentation, hosting that. Really appreciate it. And Eric, thank you for all the AV work that you're doing. Did I miss anybody? Mark and Charlotte, so good to see you guys back with us. So great to have you. So let's adjourn with that and enjoy some refreshments and hustle on out of here. So thank you all on Zoom for joining us, and we'll see you again next month. Hey, Jerry.